I guess we can start. Hopefully the spring break was nice for everyone. So, as you may remember, before the break, we already finished all the material for the second midterm. So the second midterm will be 2 weeks from today, during this class hour. I sent an announcement like before the break with some information. What we will do is that on this Wednesday we'll have like a review session. So like if you check the announcements, I also told you which problems I was planning on doing. Most likely I won't do all of them here. Like my plan was to split that review session between your class and the other class I'm teaching in 250. So like what I'll do is also record that other class. So that way you can kind of watch that other video and it's like different problems from the ones I'll do on Wednesday. So I'll teach that the second class of the week with them is like on Thursdays. So after Thursdays, I would have like the second video for the review session. So I mean, it depends on when you start studying for the midterm, whether you would like to watch it right away or not, or you prefer to wait. But yeah, at least for Wednesday, I'll do some of the problems, and on Thursday I'll do the others. But I'll send you the video link. I'll just post it on the YouTube page as the regular videos that I record here. Still, I will do. I mean, the structure will be very similar to the first midterm, so it will be like 6 problems, and now, like before, I'll just take 2 from the PDF problem guide. So that if you go through all of them, you have at least a third of the exam under your control. And then, I mean, the other 4 problems, they won't be that different from the stuff we have been doing. So it's like, it was kind of structured very similarly to how I did it for the first midterm. That really, like, the determinants is not as important. I mean, it's just like an easier topic. So like that probably would be like 2 problems out of the 6. And then this stuff about finding bases, vector spaces, column space, row space, and all that stuff will be like the remaining 4. So the split is like 2 and 6, 2 and 4 basically. Okay. Any questions about that? But again, I will still have 2 more weeks, so that way you still have time to prepare. But we're kind of, I mean, since it's like the first time I have taught this class in a long time, and first time here at Rutgers, so I'm not sure if we are ahead of schedule or not, but at least like you have 2 weeks to study for them, which is good. Plus the spring break if you use the spring break to study. Hopefully you did, but if not, that's fine because it's not over. So today, as I said, with new material, so this is going to be only until the final. We have to talk about eigenvalues and eigenvectors. This is one of the like more interesting topics of linear algebra. I'll make you watch like a YouTube video if you want, so that you see some of the applications. Some maybe we'll do next week, depending on whether or not we'll have time. If not, we'll do it after the exam. But for example, like when you have like a number a scalar, you can take it like e to the a or cosine of a, sine of a, right? Like you can have evaluate like these functions at a real number. Well, there's actually a way to do the same with matrices. So there is a way to talk about the exponential of a matrix, or the cosine of a matrix, the sine of a matrix, things like that. That is slightly more complicated, as you might imagine, on how it needs to be done so that it gives you something reasonable. But after we have talked about eigenvalues and eigenvectors, you'll see that there's like a cool way to do it using that. So we'll do that as an application of this topic. But again, like probably maybe next week if we have time. Otherwise, I'll explain it after the on how to do this. But they really should like have a lot of other applications This is like more like a mathematical application, but you know, like in physics and other places, they also like show up quite frequently. So let me explain what the idea behind them is for now, and also for the majority of the rest of the course. Like typically, A will be like a square matrix. So A is here a square matrix. So why is that useful? That allows us to go back to this. Well, if you go back to the beginning of the course, right, where we talked about the matrix as like some sort of process, the idea in this picture was that you started with a vector v, and then you think of the matrix as some sort of process, right? And the output that it produces is a vector av. So this is the input, and this is the output. Okay, and that is actually true in general, regardless of whether or not the matrix is a square one. The thing is that when the matrix is a square matrix, so when A is a square matrix, um, both the, let's say, an n by n matrix, what happens is that both the input and the output have the same number of entries, right? So the vector that you start with has n entries, and the vector you end up with has n entries. So they are of the same size. So that's useful because that means that you can actually draw the two vectors on the same space if you want. So for example, if you had like vectors with two entries, and you're dealing with a 2x2 matrix, maybe here's the vector E somewhere here. And maybe the vector AV would be somewhere like this. Right, that would be in the 2x2 case. In the 3x3 case, like maybe like the vector B looks like this. Let's see. Let's make it a little bit bigger. And vector AB will look like that. Okay, so what I'm saying is that when A is a square matrix, then you can sort of draw both the input and the output in the same picture, on the same picture. Um, that allows for the possibility, um, which you shouldn't expect it to happen in general, but it allows a possibility for B and AB, so the input and the output, to both point in the same direction. Okay, so there is a chance for B and AB to point in the same direction. Well, not so much to point in the same direction. What I really mean is for them to be parallel. Okay, for to be parallel. So what happens when they are parallel? Just to do like some pictures before writing these more algebraically. So when these are parallel, here's like maybe AB, and there would be like the vector AB would be in here. Or when they are parallel, maybe they look like this, or So this just means that you can sort of draw them on the same line, the two vectors. And so if that happens, you want to say that V is an, when this happens, you would call V an eigenvector of the matrix A. So if this happens, V is called an eigenvector of A. So far, so good. Any questions about this? So this again, like this point about eigenvectors is looking. We're trying to look at vectors, trying to find vectors as inputs whose output points in the same direction, basically as an original vector, or like that the output is parallel to the original vector. So both input and output become are parallel vectors. Okay, so mathematically, what was the condition to check? Like, how would you check if two vectors are parallel or not? What's the way to check that? Or what does it mean? What did it mean for two vectors to be parallel?
The scalar multiple.
Right. Well, then, like vectors are parallel. That means that they point in the same direction. Like, so what this is one vector and this is the other vector. That means that you can enlarge one of the two, or maybe shrink it if necessary, to get to the other one. So the way in which this is written, so one is like a rescaling of the other. So one is a rescaling. So the way in which this is typically written is that you have AB. So the output should be a multiple of the input, a scalar constant, the input. So this means, so we must have this where this constant, which is typically called lambda. So lambda here is like the rescaling constant, or like a rescaling factor. So it's a number. So it's a scalar or number. And that's actually what's called the eigenvalue. So this is called the eigenvalue of for the eigenvector B. Okay. So in this equation, lambda is the eigenvalue. Let me put it here one more time. V is what you would call the eigenvector. Does that make sense? Let me give you a second to copy this. So finding eigenvectors and eigenvalues just means, can you find a vector again that becomes parallel such that A times B is parallel to this vector? So let me give you an example to make this a little bit more geometric, and then I'll give you more of a criteria to find this stuff. let's make things a little bit more concrete. So yeah, let me do these two examples. So here's example one. So for this one, I'm going to start with a vector b, right? For convenience, I will just write it in terms like as column vector. And the matrix, like the operation of this vector, what it will do is take this vector and reflect it across the x-axis. So I don't know if you remember, like at the beginning of the semester, we kind of found like a vector of this form, right? So we would take a vector, and if you imagine you put like a mirror across the x-axis, you look at its mirror image, right? So the mirror image would be roughly of this size, but the matrix will also double the vector in size. So I want my new vector to be 2x minus 2y. So this involves like a reflection, right? Or like the mirror image of this vector, but in the mirror, it just looks twice as big. That's basically what this matrix is supposed to do. Okay, so if you remember, like this was like the typical midterm problem. Oh, I mean, there was like a midterm problem which was like find the matrix that would take the vector x, y, for example, to the vector 2x minus 2y. And if you do, I mean, this one is not too bad, but if you find this matrix, it would be 2, 0, 0, negative 2. Okay. Right, so if you do this matrix times xy, this times xy, you get 2x minus 2y. Right? Is that making sense? So far, so good. So if I ask you to find eigenvectors of this matrix, I'm basically asking you to find a vector whose mirror image, or rescaled, a large mirror image if you want, points in the same or is parallel to the original vector, right? So is there like a vector with this property in this picture that you could imagine? Geometrically speaking. What do you think? Yeah. Um, great remark. As a condition, let me put it as a we always ask B to be non-zero. That should I have said that? You reminded me, so I'll always be. We require the different from the zero vector. Otherwise, like yeah, many cases just will become very silly. Like the zero vector kind of like ruins a lot of things. Like for us, if we allow this. So yeah, we have to find like a vector with some size. Yeah. Right. If you, let's take something along the x-axis, right? So here's an example. Take the vector, like for example, 1, 0, right? What would the vector A be? Well, AD is the mirror image, right? Like, but it's like along the axis of where the mirror is taking is being placed. So nothing really affects like how where this is pointing, and it's just going to make the second entry twice as large. So like the a large mirror image is 2, 0. Is that making sense? So if you see, if you compare the green one versus the orange one, like the only thing that happened in the effect was just rescaling this by a factor of what? What would be the factor of rescaling? It's just 2, right? So like that means that what I want to say is that 1, 0 is an eigenvector of A, and the eigenvalue corresponding to this eigenvector is 2, because you had to multiply by like the length by 2. So Is that making sense? So far, so good. No, the question is this like the only eigenvector in this example, or are there more? Yeah. Well, there are infinitely many options. In fact, like, any multiple of this one would work. So just to make it more concrete, like, if you take V to be, I mean, it doesn't have to be along the positive x-axis, right? You could take V to be like -2, 0, right? And AD still, if you look at the formula for AV, is now -4, 0, right? So it's still like a rescaling of 2, right? And it's still pointing, they're parallel to one another. So you want to say that B -2, 0 is an eigenvector of A with the same eigenvalue, right? Is that making sense? So like, as an analogy, I mean, you could imagine like a family. So like your parent, like you have some siblings. So uh, all of you would share the same last name, right? So like you have the same eigenvalue, this analogy, but there could be different eigenvectors. So like the eigenvectors are like the first names, right? So if your parents didn't want to make their lives hard, like they would name each of you with different first names, right? Otherwise, that would be confusing. So like the first names can be the eigenvectors, right? So what I'm saying is that there can be many eigenvectors associated to the same single eigenvalue, as you can see here. So many different first names, but the same last name in that way. Okay. So in fact, like this rescaling kind of shows you something else, which is an important property. Let me write it explicitly, which is like if you find an eigenvector, any multiple of that will still be an eigenvector associated to the same eigenvalue. So let me write that as a remark. Well, any non-zero multiple, because again, we don't allow the zero vector as an option. So if B is an eigenvector of A, with eigenvalue lambda, right? Then any non-zero multiple of B continues to be an eigenvector of A with the same eigenvalue. It's kind of what was like, it's a generalization of what happened here. Then any non-zero multiple of B is an eigenvalue of eigenvector of A with the same eigenvalue. Is there any questions about this? Okay. So let's do another example before I give you more of a criterion for finding eigenvectors and eigenvalues. So let's keep doing some other examples. So here's example 2. Well, if you remember, we had this rotation matrix from the beginning of the course. This should correspond to a rotation counterclockwise by an angle of theta. Just to make things more concrete, let's say that theta was pi over 2, so I want to rotate things by 90 degrees. So let's take theta equals pi over 2. So if you take theta equals pi over 2, this matrix becomes 0, -1, 1, 0. Okay. So pictorially, what's happening here is like this rotation matrix, right? It takes a vector v and rotates it counterclockwise by 90 degrees. So in fact, makes it perpendicular to the original vector, right? Although that's less important now, but like there's a 90-degree angle here, right? So if I ask you, are there eigenvectors for this matrix? What could well, maybe the answer is in this case. What do you think? You're right, but well, we will get to that, but we will exclude them for this course. So, but if but just from the picture, it looks that no, right? Because the moment you rotate it, like almost by definition, like it's just pointing somewhere else, right? Like it cannot be pointing in the same direction, right? Like when you make a rotation, like for example, by 90 degrees. So this picture seems to suggest that there is no eigenvectors, right? So it looks like from the picture, it looks like there should be no eigenvectors. Okay. And that's more I mean, that will be true, but let me will become more clear by the end of the class when I give you like a more concrete method to find it for finding eigenvalues and eigenvectors. But for now, let me do it a little bit more by hand, just from like this particular case. So how to see the like if you wanted like a better argument, like a more written out proof. So here's like the proof that this doesn't work. What am I going to do now is do something that's called proof by contradiction, which is a technique that very common in mathematics. Maybe you haven't used it that much, but I'm just saying, well, let's just assume that there is this miracle eigenvector. So let's just assume by contradiction that we do have like an eigenvector, right? That we have an eigenvector. So what does it mean to have an eigenvector? It means that you have like this equation, AB equals lambda B. We have an eigenvector, we have eigenvalue lambda. So let's call this the equation star. So we're pretending that there's an eigenvector, so that means that should be satisfied. Okay, so what I'm going to do now is a trick, because like, well, this is an equation, so you can multiply an equation both sides by something that's useful. What's useful in this case is to multiply again by a. So the trick is to multiply both sides by a. And I'll emphasize that by putting this extra a with a different color, so that you see the effect. So. Okay. So let's just work out what happens with each side of the equation. So this just becomes a squared b, right? A becomes a squared b. And how can I rewrite this? How is there a way to rewrite the right hand side?
You can pull the scalar.
Yeah, the only thing I can do at this point is kind of take the scalar out of the multiplication. Remember, that's something you can do with the scalars. So this becomes lambda AB. That making sense? So far, so good. Okay, and now let's start working out each side again. So what is a squared? What is a squared? Is, well, it's a times a. That would be 0, -1, 1, 0 times 0, -1, 1, 0. So what does this give you here? What do I put here in the first entry? I think someone said -1, right? In this one. 0. Good. Good. So it's minus the identity matrix, right? Which makes sense because this is rotation over, this is rotates 90, this rotates 90, so you're rotating 180. So when you rotate something by 180, you just change both entries by a minus sign. Okay, so that means that a squared is minus the identity. And what is lambda AB? We know that AB is lambda B because of the equation star. So this becomes lambda times lambda B. And here I'm using star. Okay. So what do we get? On the left-hand side, the identity, remember, is there whenever you need it, but you can also make it go away. So like you don't need to write it explicitly because it's kind of like the number 1. So this is just really minus b. And lambda times lambda is lambda square b. Okay. So the good thing of doing it this way is that now I have an equation just for b. Before I always had the matrix A involved. I kind of got rid of it by playing with a little bit with the equation. And so what can I conclude about lambda squared from here? What should that equal? It has to be -1 because b is non-zero. That's why you need b to be non-zero, because if b is 0, it's just telling you 0 equals 0, which is silly. But and then this answers comes back to this question. We are trying to find a scalar or a number whose square is negative, and that's kind of not allowed for us just because this course is basically real numbers. So this we cannot solve because we're not allowing complex or imaginary numbers. So we can't solve this since we won't use complex numbers. For those of you, I hopefully by now everyone did them at some point in high school, but if you haven't, then don't worry. Or imaginary numbers. Okay. That makes sense. So it's a little bit I mean, from the picture, it was kind of clear that there shouldn't be eigenvectors, but if you want like a more decent proof, that's more or less what you would do. Obviously, still a bit. It's not like an obvious proof to do. but it's also not too bad, but it does give you like a flavor, like a sense of like how these proof by contradictions look many times. Uh, okay, anyone else? Questions? Okay, so now we have a better idea of like these eigenvalues, eigenvectors. Again, you're just trying to find vectors that remain parallel after you do the multiplication. So there's like a better way to find them. So let me a useful way to find these eigenvalues, eigenvectors. So again, like the idea is that for an eigenvector and with this eigenvalue, you should have this equation. Now I'm just going to rework it so that it's kind of more obvious to see what's going on. So one way to rework with this, work again with this equation is just move everything to one side. So this is, if you subtract lambda v, this is equal to 0, but just be careful because it's a 0 vector, not like the number 0, but it's not like a big thing, big deal, but it's important to keep it in mind. Okay. So the advantage of doing this way is that you see a v on every factor, so you can factorize it. And this is almost correct. The problem of how I wrote this is that A is a matrix, lambda is a number, so you cannot quite subtract a number from a matrix, but there's like a very easy fix that you can do here to make this correct. So what can you put there? Yeah, you can put it because again, like you should always think of the identity as being there if you need it. So if you do like when you multiply identity times v, it's just v, so it does give you back the previous equation. So now this is correct, and a minus lambda I or a minus lambda identity makes sense. Okay. And why is this useful? Because this is saying that v solves an homogeneous equation. And so it brings us back to homogeneous systems. So you see, like everything in this course is just a repackaging of systems of equations. It's just like you reuse them in more interesting ways, but it's really always the same ideas. That's a nice thing about linear algebra to some extent. So so V is a non-trivial solution. So V would be a non-trivial solution to this homogeneous system. Okay. So now, is that making sense so far, so good? So now you have to go back to the material of midterm 1. When does a homogeneous system have a non-trivial solution? What had to happen? Yeah. It's related to that, but I want to say it in a slightly different way for now, but then I'll get back to someone else with the same. Has to do with the nullity. So what has to happen with the nullity? It has to be positive for like there to be a non-trivial solution. So this needs, so we need the nullity of a minus lambda I to be positive. Because if the nullity were 0, then the only solution would be the 0 vector. But the thing is that since this is a square matrix, this can be written in terms of the determinant. Okay, so since we're dealing with square matrices, there's another way that's convenient to say this. We can say this if this is the same as. So there's something about the that I can say instead of about the determinant of this matrix. What should happen with the determinant? What should this? It has to be zero because if it were not zero, if this is not zero, this determinant is not zero, then this matrix is invertible. The moment this matrix is invertible, then you can multiply by the inverse on both sides, and then you would get b equals zero. So you need the determinant. You have to force the determinant to be zero to have a non-invertibility and have the possibility for interesting solutions. Okay, and this equation will be the basic equation actually for finding eigenvalues. It's called the characteristic equation. So like I'm about to apply it in a couple of examples so that you see how it's used. But so this is another reason why the determinant thing was used important in this course to just find eigenvalues. So this is called the characteristic equation. So far so good. Any questions about this? So let me give you some examples. So here's example one. This is our previous matrix of rotation by 90 degrees. So that we already know a little bit about this matrix. So it's good to kind of start with somewhere that's familiar territory. So this is rotation by 90-degree matrix. Okay, so how does the equation look like in this case? You are doing A minus lambda identity. Sorry, I mean, what happens, I should say this. What happens when you multiply lambda times the identity? Every entry along the diagonal gets multiplied by lambda. That's why I'm writing it this way. So this is lambda times the identity. So it becomes negative lambda, negative 1, negative 1. Is that making sense? Kind of reasonable, right? So the characteristic equation, that's also sometimes called the secondary equation. If you take differential equations, there's a similar equation at some point that you have to solve when you solve linear equations. This is kind of where it comes. I mean, it's all related. Um, so, so the determinant of A minus lambda I. Well, the determinant is easy. It's minus lambda times minus lambda, that becomes lambda squared, and this becomes plus 1, right? So we would need to solve. So we need to solve lambda squared plus 1 equals 0, which gets us back to the previous thing that we found before, like lambda squared equals minus 1. Right? And we already knew, and again, because we are not allowing imaginary numbers, this wouldn't work, right? So it doesn't work, but you see, it's a slightly different way from like the approach that we did last time with, which is a little bit more clever. This is like more like, oh, find out the determine and then set it equal to 0. The other one, this proof by contradiction, was more like elegant. So it kind of, I mean, here we get like the same information as before, that there were no eigenvalues for this matrix, right? But again, it's just a little bit easier to do it in terms of the determinant stuff than the other way I think I done before. That making sense? Yeah.
So once you find lambda, will you just plug that back in to find the eigenvector?
Right. I guess because yeah, that's essentially what we would do. In fact, you just kind of find a null space because it's a solution to a homogeneous system. That would tell you actually that there are like some vector spaces in the picture, because a null space was a vector space, if you remember. But right, we'll do that next week because on Wednesday we have the review. So and today I don't think I'll have enough time to tell you how to find the eigenvectors. But yeah, the idea is like, once you find all the eigenvalues solving this equation, you return to this thing, plug the corresponding eigenvalue and solve the homogeneous system. And that's how you find the eigenvectors. But like the important thing is to find a basis, because as you saw from the first example, sometimes you can have multiple eigenvectors for the same eigenvalue, and that's not something you care too much about. You care about a basis for like, but again, yeah, I'll tell you all those details next week after the review session, because for the midterm. But that's essentially what you would do. Is that making sense? So yeah.
Will we be doing this with 3x3?
Yeah, it's not sometimes like the matrix, if it's 3x3 or 4x4, to make it efficient, like you kind of put like, you know, zeros somewhere so that it's not bad. Like yeah, what would happen? I also would write that in a couple minutes. So for example, if this were 3x3, the polynomial that you get is cubic, if that makes sense. And so yeah, how do you solve like a cubic equation, right? Like a cubic polynomial equal to 0, that's not so easy. So like it has to be like an equation where you can factorize. It usually is something where it's relatively straightforward to factorize and things like that. I mean, there is a formula for the cubic equation, but that's kind of like a pain to find. There's actually like that's actually why imaginary numbers were discovered. I'll make you watch a YouTube video about it. It's like by this Veritasium, which I don't know if I already asked you to watch from his channel, but it's pretty good. So it's fun because it's related to the Renaissance, like, and people had duels in those days to get tenure. So like you were a mathematician and you would challenge someone to a duel to be like the mathematician of the court. And yeah, it's like a long story, but it's kind of fun to see what people had to do those days to survive. But yeah, like when it's 3x3 or 4x4, like typically I would give you like something where it's easy to solve the equation. But the 2x2 case is kind of that's more or less no problem, because you do have the quadratic formula for finding the roots of a polynomial, so it won't be bad. So here's example 2, which is our matrix from before, right? This was a matrix that reflected along the x-axis, right, and doubled the vector in size. So this is also one that we did study before. So what is A minus lambda I? That's 2, 0, 0, -2 minus lambda I, which is this. So you get 2 minus lambda, 0, 0, minus 2 minus lambda. Is that making sense? So again, you take the determinant of that. And this determinant is kind of easy. Okay. And then I'm asking, when does this become zero, right? So when is this zero? The characteristic equation is asking you to set this equal to zero. So lambda equals 2 is a possibility, and that's like the eigenvalue we had found at the beginning of the class, right? Like lambda equals 2. And there's this other one, which would be what? Lambda equals -2, right? Here you can find like the lambda equals -2. And that we didn't at least see so directly from the picture. So we will have to get back. Eventually, we will return to this case to see where this other eigenvalue is showing in the picture, right? But like, at least when we discussed this matrix, lambda equals 2 was pretty clear, but then there was this other one hidden. So this is why it's important to have like an algebraic method to find out the eigenvalues, because if you just go by the picture, you could just like forget to identify some, if that makes sense. Is that okay? In fact, before continuing with a more interesting example, here's a remark I can tell you. So like this matrix is diagonal in the sense that like the stuff outside the diagonal is a bunch of zeros. So here is something that's useful. Let me make it as a remark. A is diagonal. Uh, so by this, I just mean that there are some there are some numbers along the diagonal, and outside the diagonal, there's a bunch of zeros. Okay, so zeros everywhere outside the diagonal. So so it's a generalization of this case, right? So what the eigenvalues for this matrix should be, what do you think? So the eigenvalues for the diagonal matrix are what? Just the entries along the diagonal, yeah, essentially. Are A1, A2 up to AN. A1, A2 up to AN. So the entries along the diagonal. Is that making sense? Because like when you subtract lambda I, you just it's that lambda I is also diagonal, so the determinant is just like very easy to compute. It's just a product of the entries. So okay, this is an example where you can very easily compute the eigenvalues regardless of the size of the matrix, the diagonal case. And next week, maybe, we'll see that like the next best thing to be diagonal is diagonalizable. And you'll see what that means. But it means that you can sort of fake it and make it diagonal like the matrix to in some clever way. And this diagonalizability thing is like the thing that allows you to compute like the exponential or the sine of cosine of a matrix relatively easily. So we'll talk about that in a couple of lessons. Okay. Let me do a sample which is a little bit more interesting from these two in terms of eigenvalue problems. So here's example 3. I'll give you the matrix. So this is one that we haven't studied today, so we don't have like any expectations of what the answer should be. So where you are, where are you? 1, -2, 1. Okay, so what are the eigenvalues here? Again, you have to do A minus lambda the identity. If you want 1, -2, 4 minus lambda 0, 0 lambda. So that gives you 1 minus lambda 0, sorry, 1 minus lambda 1, -2, 4 minus lambda. Right? You find the determinant of this. Um, well, so this gives you 1 this gives you 4 minus lambda minus 4 lambda plus lambda squared plus 2, right? And that's what lambda squared minus 5 lambda plus 6. And if you factorize this one, it's lambda minus 2 times lambda minus 3, right? And so the eigenvalues are 2 and 3 in this case. Okay. So notice that, like, in general, these eigenvalues are not related at all to the entries of the matrix, right? 2 and 3 are not even in any of the entries. So there are no rules except, like, for example, in the diagonal case and other special cases where you can just read off the eigenvalues from the matrix, right? That's why the diagonal case is kind of useful, because to find them, you can just read them literally from the entries of the matrix. Does that make sense? Okay, so well, now you are getting hopefully like a better sense of how to find eigenvalues. You will get like to some polynomial, right? And you have to do either factorization or something like that to find the roots of that polynomial. So like that's more or less what happens in general. So let me give you some other facts which are useful. So some other facts. So for an n by n matrix, matrix A, uh, this equation is the equation for a polynomial of degree n in lambda. So it's like an equation, it's a polynomial equation. It's an equation. So again, this means that for the 2 by 2 case, you will get like a quadratic polynomial. For a 3 by 3 matrix, you will get a cubic polynomial. For a 4 by 4 matrix, you would get a quartic polynomial. And then after that, I don't think there's like a name for special names for the others. But if you know this, like a quadratic polynomial has 2 roots, right? A cubic polynomial, well, has 3 roots. Really, if you allow complex imaginary numbers. But like the important thing is like it has at most 3 roots. A quartic polynomial has at most 4 roots. So what I'm trying to say is that at the end of the day, this is telling you that there are at most n eigenvalues. That's the important thing. So that gives you like an important result because it's like there is only a finite number of eigenvalues at any given moment. So, so, so there A has at most n eigenvalues. So 2 by 2, 2 eigenvalues, 3 by 3. The max is 3 eigenvalues, 4 by 4. Max is 4 eigenvalues, and so on. So that's very useful. Yeah.
If we get like a specific cube, we can insert one real.
Right. Like in that case, for our course, we would say that there's only one eigenvalue. Yeah. Exactly. But once you allow for imaginary numbers, then there would be 3. Yeah. But the important thing is more like yeah, that it gives you like the upper bound in the sense like we know the max number of eigenvalues in general. No, but yeah, that's a good point. Yeah, okay. And just as a remark, which is kind of useful, it's like more like a sanity check that you can use it if you want to check your answer, whether or not it works. So here's a good remark. If we allow these complex or imaginary numbers, right? So if we allow, so it's a little bit of a cheat, but you're free to use it. So if we allow complex or imaginary numbers in this course, the matrix A would always have n eigenvalues. The things that some may be repeated and some may be imaginary or complex. So A would have n eigenvalues. Repetitions are allowed, so it's fine for one because even for polynomials, like sometimes the roots are the same, right? For real roots, so with the repetitions allowed. And a very cool property that these eigenvalues have, like, is that the determinant of the matrix A is a product of the eigenvalues. So the determinant of A is lambda 1, lambda 2 times lambda n. So, and I'll show you this with these examples. And the sum of the eigenvalues is what's called the trace. That's just like this is just the sum of the entries along the main diagonal. So for example, so just to give you a better idea of what I mean by this, if you look at this matrix, what's the determinant? The determinant of this matrix is 4 plus 2, which is 6, right? And the trace, this is called the trace, is like the sum along the main diagonal, so it's 1 plus 4, which is 5. But in this example, we had 2 eigenvalues, right, which were lambda 1, lambda equals 2 and 3, or the eigenvalues. Right, so if you do 2 times 3, you get 6, which is the determinant. If you do 2 plus 3, you get 5, which is a trace. So that's actually does work in general. So like the sum of eigenvalues gives you the trace, and the product of the eigenvalues always gives you the determinant of the matrix. And in more elegant courses, you could define the determinant of a matrix as the product of the eigenvalues. If you really wanted to restart this all like backwards, it's very elegant to do it that way, but I mean it's fine like the way we did it also. So if you take like the rotation matrix, right? The determinant of this matrix is what is 1, and the trace is 0 plus 0, which is 0, right? And the eigenvalues here, like this is why I'm saying that you would need like complex numbers. So the eigenvalues would be I, which is the root of -1, square root of -1, and -I. So right. So if you if you add them together, I plus minus I, you get 0. And if you multiply them, you get I times -I, so that's minus I squared. And if you have worked with these things, like minus I squared is just 1. So it checks out. For the other matrix that we use, like 2, 0, 0, -2, right? Like the determinant was, well, this one is easy. It's like just -4, and the trace in this case is 0, and the eigenvalues were like 2 and -2, right? And yeah, I mean, it was just a product of, I mean, the diagonal case is kind of straightforward because like the determinant is just the product of the entries, and the trace is literally just the sum, and they coincide. But it's still, I mean, useful to write it down explicitly. So it's more or less like saying that this formula, which is this property, which is more or less obvious for the diagonal case, continues to hold in the non-diagonal case. Yeah.
Can you use that to like find the eigenvalues just by doing like the average of the trace plus and minus the square root?
I mean, like for a 2 by 2 matrix, you definitely can use these two formulas to find the eigenvalues. I don't think it buys you that much time because I mean, you get like in the 2 by 2 case also like the quadratic equation is
Yeah.
more or less. I mean, if you don't buy yourself too much time, I see it more or less like a sanity check in the sense like, well, even a 3 by 3 matrix, right? You in principle could have 3 eigenvalues. So if you multiply those 3 eigenvalues, you should get back the determinant of A, and if you add them together, you should get the trace. So, but yeah, you can use it to at least in the 2 by 2 case to completely find the eigenvalues, but it's not too much of a gain in general. So I mean, for like when the trace is 0, then it is a gain because that just tells you the one eigenvalue is minus the other, for example. But except for that, like it's not. But it's just kind of useful, interesting to know that this is true in general. So okay, yeah. So again, as I said, this is more or less everything that you need to know to find eigenvalues. You always have to solve like the equation of determinant of A minus lambda I equals set it equal to 0. That's how you always find it. So what I'll do is like create like one of these mini Canvas assignments just for you to do some practice with 2 by 2, 3 by 3 matrices so that you're gonna get used to it. Again, like with the 3 by 3, even there you have to be careful because cubic polynomials, again, like finding the roots of a cubic polynomial can be tricky. But so on Wednesday we'll do the review for the second exam, and so once we get back to this next week, I'll tell you, okay, so now once you have the eigenvalues, how do you find the eigenvectors? And then how do you use them for useful things? Okay, so it would be fine. It's interesting just because again, finding eigenvectors is finding the null space of something. So it comes back to this stuff that you need to know for the second exam about finding null spaces. Okay, so it is useful to that extent. But yeah, I think this is a good place to end. So I'll see you on Wednesday then for the review.